All right, so I'm Michael Hennecke. I'm the Chief Technologist for HPC Storage at Lenovo, and I'd like to go through a few topics that we worked on together with the Intel team in our benchmark center, which is located in Stuttgart. So we have a system of 12 DAOS servers, which are our 1U 2-socket servers, like nothing special. Just because we have everything in 1U, we are a little more concerned about thermals. We run the standard Intel P4610 NVMe drives and the usual Apache Pass DCPMMs. Our system is, on one hand, a production system. All of our benchmarkers are using that to do application benchmarks for RFP work, so it's very important that the system is up and reliable. On the other hand, on the storage side, it's also a lab where we experiment with new technologies, but we really want to run it as a production system and not introduce a lot of risk, and our application specialists do not have root access to the servers, right? So we have to really run in a situation like a customer would do this. We have been running with 101 for quite some time, and a few weeks ago upgraded to 111, and all of our systems are using systemd to start and stop the daemons. So I did show the internal server design on the last DAOS user group, so I don't want to go through all the details here. Just wanted to highlight that we use 2-socket systems with 1 InfiniBand EDR link on each socket and 4 NVMe drives on each socket. So there's balance between network and NVMe bandwidth, and for these tests that I'm showing here today, we are populating all 12 DCPM MDIMMs. So one thing that was really key for us was to integrate DAOS with Slurm. We are right now providing a number of different DAOS clusters. And somebody mentioned earlier that the names of the clusters, actually in DAOS 1.0, you couldn't change the names. So the only way to do this is to actually change configuration files on the fly and point them to different systems. We're using Slurm licensing features, so the user can select which DAOS cluster they want to use. There's always like a DAOS_Mellanox, which right now is an 8-node cluster, and we have a bunch of development clusters, which are typically individual nodes that people are using to run special tests and special configurations. So we just use Slurm, so we can submit like 100 batch jobs, and they all run one after each other, and people don't step onto each other. And the user uses the SBatch license feature to select which cluster they want to run on. And then we hook into the Slurm prolog and epilogue, we hook our own mount script. That mount script in the prolog phase goes in, sets up the YAML files that point to the right servers with the right IP addresses, and they're all called DAOS server, right? There's no, the name of the clusters are all the same. Starts the agent, then provisions a pool, provisions the container in the pool, and saves the UUIDs of the container in the pool. I come back to that a little later. And then finally fuse mounts the POSIX container for the user in a predetermined path. And in the epilogue, we unwind the same thing, right? We unmount the container everywhere, and then we're destroying the pool and removing the files that we use to communicate this stuff. And I'll come back to those files on the next slide here. So this is something we use for other file systems as well. And we've done the integration with DAOS with the capability to talk to essentially multiple DAOS systems. So if we look at the details of what's in that mount script, it's the standard stuff, right? We do a DMG pool create. The prolog runs as root, but we know the user ID and group ID of the user who starts the job, right? So we can create the pool that's owned by the user. Then we are updating the ACLs on that pool, because root is not a special identity in the DAOS security framework. So if we don't give root access to the pool, we get problems later on in doing root level provisioning on this. So we do an update ACL, and then we have to do an SU minus to the user ID to create the container and to do the defuse mount. If we try to create the container as root with permissions for the user, but that has caused quite a few, like, very, at least for us, unexpected behaviors, and we are in discussion with the Intel team about this stuff. So our best approach really was to change to the user ID of the end user and do the container create and the fuse mount here. So there's one gotcha in this sequence here. All of the steps except for the last one you do on the single node, right? The batch host, the node 0, if you will. But then everybody needs to mount And if you don't use this unified namespace concept, how do the other compute nodes in your job learn about which container and pool ID to use? Our initial approach to do that is by just creating a .daos directory in the end user's home directory, and save those pool and container and service replica IDs as files in that doc directory. And then this is in our GPFS home directory, so it's available on all the compute nodes, and all of the participating nodes in the job can actually read those files and then do the fuse mount. So that's our non-integrated, non-namespace integrated way to save that information. And it works quite well. But the second topic I want to talk about is actually going back to the unified namespace model, since, I mean, we do a lot with Spectrum Scale or GPFS, right? And we actually tested and like brought this up with GPFS as the global file system. So unified namespace for us really is two things, right? It's you can store the UUIDs in the extended attributes, and then at mount time, because that file system is a shared file system, you can fetch those UUIDs on all the nodes that need to mount in a parallel job, instead of passing around those container and pool IDs. And you see the same container create here as before, right? The difference is that now we have a pass that we give to the container create command, just like what Mohammed showed a few presentations back. And DAOS will create this directory and store the attributes that it needs for this unified namespace concept as standard extended attributes. So this is a DAOS command, right? The DAOS container create with the path name of a directory that lives in the Spectrum Scale parallel file system. And now I'm showing two MMLS attribute calls. Those are Spectrum Scale commands, right? To list what extended attributes do I now have on this directory, and what are the values of those. So I can dump the attributes, which just gives me the list of all extended attributes that are attached to the directory. And that's really the only special thing. Other than that, that directory is just an empty Spectrum Scale directory, right? It has no special features. And then with the MMLS attribute get attribute, I can fetch this user.daos extended attribute, and it gives me like an URI that includes the pool and the container information. And at the end, there's a question mark, which I suspect is just like a null termination or something fancy that the command here can't print out. So that's what I see on the GPFS side, right, on the Spectrum Scale side. And now if I use DAOS again, I can do the DAOS container query, and I just give it the path, right? I don't need the pool and container anymore. And by looking up the path, I get this URI that's stored in the extended attribute, and I can recover the pool and container ID. And defuse can do the same thing. So instead of giving defuse the container and pool, I just give it this mount point, essentially. The mount point is global in my whole cluster. So at least with this mechanism in Spectrum Scale, I can make it easier for the user to pass around that information. What Spectrum Scale does not provide, which I think is at least in the roadmap, if not already implemented on Lustre, is the transparency of if you change directory into this after it's mounted, then Lustre will do much more to enable transparent access than what Spectrum Scale at this point is able to do. But we have started some discussions with the IBM team about, can we make this easier for the Spectrum Scale side as well? This service replica option, as we see here, that I didn't highlight in red, this is going away in 1.2, so that's why it's not integrated in this namespace work here. It will just become redundant in a future DAOS release. So this worked all quite nicely. There's one strange gotcha that, Johan, we have to work on to figure out what's happening. On all of our compute clusters, this works just fine. On the DAOS nodes, we are actually root squashing the mount of the GPFS file system. And if we do that, I can mount, but I can't unmount from the GPFS file system because there's some strange permission problem that just fails the fuser mount 3.u. So not a problem in operation, but on the nodes where we have people with root permissions that shouldn't have root permissions on our global file systems, this has actually caused some hiccups. And the only way to recover right now is to reboot the node. But other than that, it's working fine. So it's a demonstration that this unified namespace concept is really not using any special stuff. It's just using standard extended attributes, and it works just fine with Spectrum Scale. All right, so let's spend the last few minutes on some performance stuff. Mohammed already showed this slide here. What I wanted to highlight in the next slide here is that there are actually 3 different arrows here going from the application and from diffuse down to the libDFS layer, right? And the interception library is available today. There were some comments also on the mailing list, and I think we've patched the documentation. You can use the interception library with 1.0 and with 1.1. And on this graph here, I'm showing the ior-easy test. The left-hand side shows writes. The right-hand graph shows reads. Single node, increasing the number of tasks on the node. If you just do diffuse, so API equals POSIX and no overloading, you get the orange line, which is like a single task is like 600 megabytes per second on writes and 200 on reads. And if you scale up the number of tasks on the node, you can get to a few gigabytes per second, but you can't get to the 11. That is the wire speed of the single client here. This is a single EDR client node, right? The purple like horizontal line on the top is the wire speed, and for whatever reason, I reach more than wire speed, so there's probably like a base 2, base 10 mismatch here in the graph. If I use the overload, like the libIOIL overload with LD preload, this is the blue curve, and this is sitting exactly on top of the green curve here, because this is sequential I/O. There is not a lot of metadata traffic, and you're actually getting the exact same sequential performance out of DFS natively and the POSIX API, including the overload. So I really encourage you, if you use the diffuse framework, use the interception library. It's worth it, and it's not really costing you anything. You can also use that on the command line, but just with the copy. Yeah, you can do LD preload equals libIOIL copy, and it's like an order of magnitude faster than just doing a normal copy. So this is encouraging, and we've also done the same experiment with the sequential IOs, scaling out the number of compute nodes, in this case here from 1 to 32. And this is just DFS. And we're coming close to, we're not completely reaching the wire speed, but there's also some other effects here that cause some slight inefficiencies. What we have observed from time to time is that there is quite some noise if you repeat the runs. In this case, I think those are 5 or 10 runs, and the error bars show like the spread of the results when you do 5 IOR runs. This is much worse with the diffuse access. It has improved significantly between 1.0 and 1.1, but we still see a large variation run to run on the same hardware when we're just using the diffuse API, with mostly without the overload library. So that's something we have to continue working on and understand better why we have those fluctuations. Even this is all simple, that this is all ior-easy large sequential. Okay, so we also run the IOR hard stuff, and what we observe here is that the single thread performance, even if you do the DFS API, is really bad, I would say. It's just like 200, 300 megabyte per second. If you get up to 14 tasks per node, you can reach a few gigabytes per second, but we have not been able with our Skylake nodes to get to the 11 gigabytes per second that we expect. We are roughly stuck at half of the performance with the IOR hard, and we'd really like to understand why that is. I'm citing here just for reference. We won't go through all the individual numbers here, of course. I'm citing full IO 500 runs that we did with a single server and 10 clients. You see the green lines without the green background, that's the ior-easy. We're getting what we expect, the 21 gigabytes per second for a single server. The green background shows the hard cases, which are like less than half of the ior-easy cases. And I would really expect that we get much closer to the ior-easy numbers. This is already using this DFS tunable of tuning the chunk size in that case, based on Intel recommendation to set it to 10 times of the transfer size. All right, so this is using the 3.2 terabyte drives, and you see read and write is roughly the same in the easy case, 20 to 21 gigabyte per second. here I'm showing if you use the smaller capacity SSDs, you always have to check the drive specs, right? The 1.6 terabyte drive only has 2 gigabyte per second write performance, whereas the bigger drives have 3. And you see this in the ior-easy right here. Instead of 2021, we're only getting 14. And that translates also to some lower performance in the other ranks here. So the overall IO 500 score of this single server goes down from 70 to like 63. But this is also fluctuating. This IO run is a single iteration. If you run this 10 times, you also get quite some spread in the total IO 500 ranking. And then last slide, and I'm done here, is showing a 9-server run that we did just recently. We missed the IO 500 list that was published yesterday, but it's still a good number on one hand. We reached a score of roughly 300 with 9 of our servers with the smaller capacity drives. But again, I mean, the IOR hard numbers are, again, roughly half of what they could be in theory. And the easy numbers are not quite at 100 gigabytes per second, which they could be with 9 servers, but slightly below. But we're still pretty happy with this, and we continue benchmarking the different cases. So in closing, I would like to really thank the Intel team who spent a lot of time working through this with us and advising us on how to change settings, how to debug issues. So really appreciate the collaboration here. Thanks, that's it from me.
Thanks a lot, Michael. Maybe we have time for one quick question. Patrick, I think you had one, maybe?
Sorry. Yes, I was wondering about, can you say more? You said API POSIX, and I'm sorry, I probably just missed a sentence. Did that mean you were using Fuse?
Yeah, so in IOR, you have an API that can be POSIX or DFS, right? If it's DFS, you have the code changes within the IOR benchmark. If you say
Right.
API equals POSIX, then yeah, this is using diffuse. So the orange curve is just diffuse. The light blue curve is diffuse plus LD preload.
Yeah, okay, that's what I thought. I was just confused by the lack of mention.
Okay, sorry, it's in the caption here, but I went too fast probably because there's way too much material for 15 minutes. Yeah,
sure,
so,
understood.
So the message here really is, if you use diffuse, right, like what we had in several talks today, you should also use the interception library. It really gives you, like you see here, at least for the sequential cases, it gives you an order of magnitude boost in performance, like a factor of 5 in most of the cases here, and you don't lose anything. It's just a simple, like dynamic redirect of the POSIX read and write calls. You still go through diffuse for all of the metadata stuff, right? So if you have metadata heavy traffic or small transactions, of course there will be some inefficiency here, but at least for the large IOs, it's pretty much identical to diffuse.
One quick comment. It sounded like your IO 500 hard numbers were using SSD. It's worth noting that the Wolf numbers from Intel are using the DCPMM, the PMEM, and that will change your hard numbers, not your easy numbers, but it would change your hard numbers quite a bit.
Yeah, understood. Yeah. Understood. Thanks.
One quick clarification. When you talked about the variance, did you say that you saw less variance with the interception library and not with DFS directly? So
I would say yes, but we have to redo a lot of this work with the 1.1 code. On 1.0.1, there was much higher variation, and it was mostly without the interception library, but we also saw some with the interception. Like on this graph here, you see for the write case 16, there's also an error bar there. It's not huge, but there is some fluctuation also on the other APIs. And there seems to be a tendency, if you do like 5 or 10 iterations of IOR, that it's getting slower over time. So there may be some background stuff that DAOS is doing, especially between the DCPMM and the NVMEs, that's dragging things down. But this is just like a hypothesis without data yet. We'll have to look into more details.
Thanks.